So good morning, everyone. I'm gonna start recording this lecture. All right.
I have one question. Is it possible for you to like upload the videos unusual so you won't have to like delete them? I
I'm
think
sorry.
that unusual. If you upload the videos unusual, you don't like the cloud is not limited, and
Oh, so you want to keep this for a while, right?
yeah, if that would be possible.
I will try. So as long as I receive any warning from the cloud, so I'm gonna let you know. Okay. So
Okay,
sure,
cool.
sure.
Thank you.
Yeah, no problem. So okay. All right. Okay, let's get started. So can you see my screen? All right. So last time on Tuesday, we talked about the maximum likelihood estimation, MLE. So I hope you had a chance to look into some online resources to refresh your knowledge about the MLE. So here in this slide, so this is the definition of the MLE. So what is MLE? So when we have a assumed model, for example, normal distribution, but in this case, the binomial distribution. So if you have a model, probability model, with this model, of course, you're going to have some parameters. So if we are talking about the normal distribution, then we have two parameters. One is the mu, which is the population mean, and the other one is sigma, which is the standard error, standard deviation. However, when we talk about this model, the binomial, so we only have one parameter. What is that? The p, right? The parameter in binomial is p, which means the probability of being successful. Probability of seeing, for example, a head showing up. So this is the model and the parameter. However, we don't know that we know nothing about this parameter. It is unknown, so we want to do some experiment so we can estimate that parameter, right? So this is what we want to do. Okay, so we will talk about this statistical inference in the near future, but now I just want to let you know our job here is to do some experiment and using the data collected from this experiment to help us estimate this parameter. Okay, so there are a lot of ways to do this, but the most popular way to estimate the parameter using your data is through this MLE, the maximum likelihood estimation. So what is that? So, okay, so here, the MLE is a method of estimating the parameters here. So for example, P, right? We want to estimate this P based on a statistical model. So here, the model is binomial distribution and the given observation. So if you do an experiment, toss the coin like 1,000 times, 100 times, you can get 100 data, right? Points. That's your data. Now, using this data, you're going to use MLE to find the parameters, estimation of this parameter by finding the parameter value that can maximize the likelihood of seeing this data. Does that make sense? Okay, very good. All right, so to help you understand this, so this is very important. Some students like took a couple of like statistical analysis classes, but even after that, some students still do not understand the theorem behind the maximum likelihood estimation. Hopefully, I can use this diagram to show you the theorem behind, and this will be beneficial to you for the whole life. All right. So look at here. So this is the case one. Case one here. Suppose this guy has a coin, so he wants to find out whether this coin is a fair one or not. So, so what does this guy have for now? What does this guy have for now? So he has a model, right? Because he knew this is a binomial distribution, and he has a parameter p. But what he doesn't have is the number of the p. He doesn't know what the real value for p, right? So that's why he wants to perform a tedious experiments to get the data and estimate that p. Okay, so this is what he wants to do. Okay, suppose we are the God. We know exactly the p value, what the value is for p. So we knew the p equals to 0.5, which means this coin is a fair one. But this guy doesn't know, so he wants to do the experiment, get the data and estimate this p. Okay, we knew this, but he doesn't. Okay, all right. Okay, now based on this situation, if this guy toss this coin diligently for 100 times. So if p, the true value for p is 0.5, so do you think the most possible outcome is the guy will get 50 heads and 50 tails? Do you agree with that? Okay, okay. Now he doesn't know the p equals to 0.5, but he will use this data to estimate p, right? Okay. Now, okay. So here is the function, the likelihood function. What is the likelihood? I'm sorry. This is the likelihood function. So the likelihood function actually is equivalent to the joint probability, which is the probability that given this p equals to 0.5, what's the chance for this guy to see 50 heads out of this 100 tosses, right? So this is the probability of that. Okay. Now, if you let p equals to 0.5, you can get a value for this function, right? If you let p equals to 0.5, then you can calculate this joint probability function or likelihood function. Is that correct? And okay, so this will give you a value. Now think about this. If you do not use the p equals to 0.5 here, if you use p equals to 0.000, a small value, so you can still get a value for this function, right? But that value should be much less than the value if you use p equals to 0.5. Do you think that's the case? All right, so now here is the function. So the function, likelihood function, actually shows the relationship between the different value of this parameter p and what value you can get when you use the different value of the p to calculate for this likelihood, right? The y-axis is actually the realized likelihood value when you use different value for p, right? Okay, now this is the function. And if you can see, if you use a very small value for p, so you are going to get a very small value for the likelihood. Is that correct? The same thing, if you use it too big, so the p equals 2 must be a value between 1 and 0, right? So if you use a very large value, which is close to 1, still, you're going to end up with a very small function, likelihood function value, right? Only if you use the right thing. We are the God. I'm kidding. So we knew the p-value is equal to 0.5. This is a fair coin. So only in this case, when you use p equals to 0.5, you are gonna get the maximum likelihood value. Do you agree? All right. But for the guy, he doesn't know. But he can. What he can do is like use this likelihood function and try different p-value and get this smooth curve. Do you agree? So he can end up with this smooth curve. And the next thing for him is to find the p-value that is corresponding to this maximum likelihood value. Do you agree? And what can we do? So in mathematics or in statistics, we can do the first derivation first the derivative of this function, right? To find the slope at each point along this function. And so if you calculate slope at here, so the slope, is this slope equal to 0? No, right? So if you keep going, the only place you can get a slope for this curve, which is equal to 0, is here, right? So that's why if you do the first derivative of this function, of this likelihood function, you can find the unique p-value, which make the slope equal to 0 here. And here is the place where the estimation of the p-value, in this case, 0.5, will give you the maximum likelihood value. Does that make sense?
Yes, could you repeat? We do the first derivative of the function.
Of everything here.
Of the entire function.
Yes, so the first derivative actually do the differentiation function along this curve, right? So look at here. So if you calculate the derivative for this function in this region, so that's equivalent to the slope, right? Is this slope equal to 0? No. So the slope is not equal to 0, it's positive, right? Something like maybe 1.5 or something. But in this region, if you do the first derivative, you get the slope which is negative, right? For example, negative something. But where is the turning point? It's here. This is the turning point. The slope along this function will turn from positive value to the negative value. Do you agree? So this is the place, the slope equals to 0, I'm sorry. And this is the place where the value for P will give you the maximum the maximum value for this likelihood function. Does that make sense? All right, so now, although this guy doesn't know the true value for this P, but based on his experimental data, indeed, he can estimate this value, and which is very close to the true value that only God knows. Do you agree? Is it beautiful? So this is actually the beauty of statistics. So we don't know the real parameter, but we can do experiment repeatedly for many, many times, get the data and use the data and then let the data speak. And then we can use the data to estimate the parameter value through this MLE. Do you like MLE? All right, good. All right, so this is the first case, simple case. Let's look at the second case. It's a little bit different. So for this, in this case, this coin definitely is not a fair one. So P equals to 0.6, which means what? Which means like it is more likely for, if you toss this coin a lot of times, it is more likely to see, for you to see heads turning up more frequently. Is that right? More often. Do you agree? Okay, now this is the truth now. So we know for this coin, the P equals to 0.6, but this guy doesn't know. So he can do the same thing. He can repeat tossing this coin for another 100 times. And let me know. So if P equals to 0.6, do you believe it is very likely that out of this 100 toss, this guy will see like about like 60 heads here? Do you agree? Right? Okay, so this is the likelihood function. Okay, now, so because this is the data, so what he observed from this 100 tosses, he observed about 60 heads, right? Turning up. All right, this is the data. And he is gonna try different p-value, different value for this parameter P doing the same way. Okay, now this is the likelihood function. So if he tries a very small p-value, so this likelihood function will give him a very small value for this likelihood, right? And if the same, if he tries a very big number here for P, so still he he will end up with a very small probability value here, likelihood. Only if this guy tries this, tries this, like the p equals to 0.6, and this function will give him the maximum value for this curve, right? Right? So now if he, so when he has this function, and if he like tries the first derivative of this function, he can find this position, this point, by looking for the slope, right, equals to 0. Is that clear? So two different situations. So depend on what the true value is. So no matter what, if we do the experiment, collect lots of data, so we have pretty good chance to correctly estimate this parameter. So this is MLE. So is that clear? Is that clear for everyone? Good, very good. Okay. All right, now back to our problem. So I usually give you very, very nice, very interesting examples, but unfortunately, eventually we will go back to our boring examples, boring problems. I'm kidding. So here, yes, last time I mentioned, so when we talk about the recombination frequency between A and B, right? So we do the experiment. We collected progeny, lots of progeny from the cross. This is back cross. So now you understand what is the back cross, right? So it's easy. So we cross the F1 progeny, which is double heterozygous, the dihybrid, back to one pure parent and produce a lot of progeny. So that's the back cross. So in back cross, if we generate a lot of progeny, we can check into we can check each individual. I'm so sorry. So I think, yeah, my connection went back, went bad. Yeah, so okay, let's continue. Sorry about this. Yeah, okay, yeah, This Zoom is very clever. I think it is still recording. Even I was not here. Okay. All right. Sorry about this. Let's continue. Let me double check. So let me see if, yeah, it's still recording. Sorry about this. This one. Okay. Okay, now, so let's go back to our real problem here. So now we have a binomial distribution. So I just mentioned when we have a progeny from, when we have a group of progeny from a backcross experiment, right? So we can categorize each individual into one of the two, oops.
Can you hear him? I cannot hear anything.
My best guess is it's possible, but maybe somebody's downloading something at his house, and so his Wi-Fi bandwidth is getting taken up by that.
It's possible.
Or it's possible multiple Zoom meetings might be taxing the bandwidth as well.
I am really sorry about this. Terrible. Yeah, I don't know what happened to my home home internet. So, did you have a good break? All right, let's continue. All right. Oops. Okay. All right. So,
Professor, question.
Yeah.
Have you
Okay.
Have you changed the slides at all, or have you shifted things around?
Yes. So
Okay.
sometimes when I figure out there's some typo or there's something so it's not that clear. So I will revise it or add a couple of more slides. But I usually I do that during the night before the lecture, and then I will upload the updated, the latest version to the iLearn. So I'm sorry about that, but so I'm learning as well by teaching. But so yeah, I always will give you the latest version. Replace the old one with the latest version on the iLearn. So I hope this will not bring too much inconvenience for you.
Nope, no problem. Just needed to know. Thank you.
Oh, okay, thanks. All right, so let's move back to our real problem again. I tried this a couple of times today. Hopefully this time will be successful. All right, so we're tossing coins. No, we're not. We're doing the experiment, the backcross experiment. And we collect a lot of data, progeny, from the experiment. And we can classify each individual into one of two categories, either the parental type or the non-parental type, right? And this is exactly the same with the experiment of tossing coins. All right, so we use the binomial here, but now we have a parameter R. So this parameter is equivalent to the P I just used for the tossing coins, right? Right. So this is the probability of showing what? Recombinations. All right, because we have two outcomes, parental type and non-parental type. And the R is actually the probability of seeing a non-parental type. Is that easy? Right? So now we have a model, we have a parameter. We can calculate the likelihood function here. And then this is the likelihood function. And because this is this equation involves the power calculation, so it's not good. It's not easy for us to do the first derivative. Then we use the log likelihood, which transform this multiplication into the sum of these things. So this is easy for us to do the first derivative. Okay, now why here? So from here to here, so we get the first derivative and set this equal to 0. Why is that? Can anyone tell me why we do this? Because we want to find the value for P or the value for R that can give us the slope equals to 0 along that curve, right? Yeah, so, and then if you do this, you can easily get the MLE, the estimated value for R. That's why we put a little hat on R. So this is not the, maybe this is not the true value. Only God knows this true value. What we can do for our best ability is to get this estimation using the data, right? Okay, so the same thing here. So if this is the function, likelihood function, we just do the first derivative and calculate the slope at each point, and this value will give us the best estimation for this R. Do you agree? Okay, now very good, very good. Okay, now we can move forward a little bit faster. Okay, so as I mentioned, for the first few chapters, I would rather to go slowly, because these are the fundamental stuff, and I hope everyone can understand this. And after that, in the future, when we move into the application, so we can go super fast. So for the fundamental knowledge, so we would rather keep slowing down to make sure we understand them well. And this will help you understand the future part better. Okay, now, so this is the first derivative, right? The first derivative is to help us to get the estimated value for this parameter. But why we need to do another derivative, the second derivative. here because we want to get this guy. What is this? What is this guy? So, because we have a r hat. R hat is not the real value for R because only God knows this value. So as human being, we can only do our best to estimate this. So the R hat is the estimation from the data we have, right? Okay, that's the R hat. Because this is an estimation, so we don't know how accurate this estimation would be. So that's why we also want to estimate the variation of this estimation. We want to estimate the variation of this estimation because this quantity will show how accurate we can do our estimation job. Is that clear? All right. Is that clear? Okay. So Fisher, actually Fisher is a very famous geneticist and also statistician. So he developed a very, very good, useful theoretical statistical theorems that can help us to do a lot of things, especially good for the statistical inferences. All right, so if we do the second derivative for this R, and if we take the expectation of this thing and do the negative minus the thing, and this will give us the information about the R. So what does that mean? The information means, okay, when you have the data, how much the data can give you the information about the estimation of this parameter. So that's the information. Information you can get from the data, which is about the parameter to be inferred, okay? And if we take the inverse of this information, that gives you the variance of this estimation, or how accurate you're gonna be able to estimate this this R. Is that clear? Yeah. Why we need to do this? Because we need this variance of this estimation, which shows the uncertainty of the estimation of this parameter. We're going to use this to construct the confidence interval. So you're going to learn about this, the confidence interval that can help us do the statistical test on this parameter estimated. All right. Also, so if you are a statistician, so anytime when you tackle a problem, so by estimating this parameter, you not only need to report this estimation, the estimated parameter, but also you need to provide plus and minus standard error for this estimation to let your client know how good the job has been done, how good this estimation is. Does that make sense? Okay. Very good. Okay, now, so, okay, again, this is about our own problem. So here we want to do what? We want to do a test. Test for what? We want to test if there's a linkage between A and B, right? So now, don't go too far. Imagination, don't go too far. Now, I try to pull you back to our real biological problem. So here, so we try to do a test to test if there's a linkage between A and B. So what you can do is to calculate R, right? Based on your data. Do you still remember how to do that? So if you got the data, if you make the backcross progeny sample population, so use that progeny, the genotype data, so you can calculate R, right? We have talked about this before, right? Now, once you have an R, you want to see if this R is close to 0.5, which shows no linkage at all, right? Or if this R is significantly less than 0.05, which shows a strong linkage between A and B. So this is what we want to do, right? Okay. Okay, so what we can do is to estimate this R. So forget about the mu zero here. So I use a normal distribution as an example, but think about like, so so if we want to use our data to calculate R here, right? Okay, so we want to use MLE to get this estimation R hat, and we can also get the variance of this estimation, right? Variance of the R hat, and using that we can construct a sorry again. I think yeah, after this class, I'm gonna make a phone call to to the internet provider, which is Cox, and figure out what happened. So yeah, this problem is new to me. So hopefully this is not too distracting for you. All right. So what was the last sentence you heard from from last time?
We were on the hypothesis test.
Okay, here, right? Okay. Perfect. Okay. Now, okay, so first we can estimate our R hat here, right? Based on our data. Do you agree? So we can use our data to estimate this guy, right? Okay, now we can also estimate the variance of this estimation to construct a distribution like this, non-distribution. So I just give you an example for the normal distribution. In our case, it is not a normal distribution, but just assume this is a normal distribution. So we can estimate this parameter, R hat, and we can construct a non-distribution, right? The non-distribution, just think about, use your imagination. Think about, this is a beautiful dress you want to put on yourself to go to the party. All right, so this is the dress. And this is the data, right? If you put yourself, the data is yourself. You are the data. If you put yourself into this address, if this RS, if it is in this region, so in this region, so very close to this R hat, which means like there's still a lot of room between you and the dress. So which is good, a good fit. However, if your belly goes to this far or here, which means, okay, the dress is too tight. The dress is too tight. The data doesn't fit the dress at all, right? So you don't think this dress is a good choice. So you're gonna reject this dress and take another dress. Do you still remember what I showed last time? Okay, thank you, yeah. So I need to see some response to make sure my connection is okay. So, all right. Okay, so what do we do here is to use our data to estimate this parameter and construct a non-distribution and use the error, the standard error for this estimation to construct a confidence interval here to do a test. So we want to use this non-distribution to test our data. If data fits this non-distribution, yes or no, right? And using this strategy to make the test, either we accept the null hypothesis or we're gonna reject it because the chance, the p-value is small. What is the p-value? P-value means if your non-distribution is correct, what's the probability you're gonna see this data based on your non-model, right? Am I clear? Okay. Our non-model is based on the R0, which is 0.05 here. But you can estimate your R hat either is here or is there to make a test core. But if your estimation from your data is go too far in this region, if you barely reach this region of
Just making sure while he's cut out, we all get this concept, right?
Yeah, I think he just cut that out again.
Yeah, but I'm just making sure that we all get this concept so we can tell him that he can move on to the next thing. Because if one of us is stuck on this, I don't want to move on.
Yeah, that's true. Yeah, that's so hard for him.
I remember reading or listening to this. Apparently, educators and TAs, we have a right to a free internet access that we can access via IT services. So if he continues to have this problem, one of us, I could probably find a link, but ITS services can provide him with a different internet service provider temporarily.
Well, I'm sure the thing is free internet doesn't always mean the best internet.
Yeah.
So you can provide him with something that connects even worse than what he has right now, but it's free.
Yeah, that is one thing I have in question because I don't know the specs for the specifications for his for the internet that could be provided, but I'm assuming it's going to be good enough for this kind of work because it's being provided to TAs like me or faculty members if they need it.
Yeah, the professor just said he need to reboost his computer, restart his computer and try to connect again.
Mm.
Yeah, maybe need sometimes.
I don't think the reboot will solve this problem because I think it's the internet is not stable, not the computer problem.
Yeah, we don't know.
Maybe we can ask him to record the lecture by himself and upload to the cloud, and we can see later.
Yeah,
if
that's a good
the
idea.
internet is not working.
I think in one of the course that I'm auditing, the professor pre-record the lecture into several mini lectures and use Yuja, and then the student can watch it whenever they want. And then he used the lecture time as a office hour.
Yes, some
Interesting.
professor will do that. Yeah, even not in this special time, I did a course and the professor will pre record the course and we just watch it beforehand and we just do the discussion in the lecture time.
So Yuja has no data cap with recordings.
Oh, really? I didn't know that.
I'm asking that as a question.
Okay.
Sorry.
I don't know.
He says a couple of minutes.
Yeah, he said maybe 5 minutes or more, because it depends on how long the restarting take.
It's nice to see you guys again. Sorry about this. I just rebooted my computer. Hopefully, I will be able to have better communication between my computer and the Wi-Fi. All right. Can you hear me? Good. Okay. All right. Let's try again. Sorry about this. Today is not a good day for me. I'm sorry about this. Okay. All right, so I think we're done with this slides, right? Okay, let's move on. Okay, this is what we have covered last time. And so, all right, so, okay, so we have two dresses here. One is the non-hypothesis, non-dress, and the other one is the dress, alternative address. So we fit ourselves into the dress, the first address, to see if we are fitting or not. So if we are within this region, so which means if we are within this region, which means, okay, our cells fit this dress very well, we're gonna accept the non-hypothesis. If not, if you go beyond this region, which means like this dress is too tight, no longer fit yourself, so we're gonna reject the non-hypothesis and take the alternative one. Okay, so all right, this is the test the guy did. And he performed an experiment to test if this coin is a fair one or not. Okay, so what he end up with this experiment is like a straight 6 heads. What do you think about this? Do you think this is a fair coin or not? Yeah, it is not, of course. But even this is a fair coin, the chance of getting a straight 6 heads is very low, but it is still possible, right? Do you agree? It is possible, but we need to make our test or judgment based on the data, based on the probability. So now we're gonna use this data to test our non-hypothesis. So can anyone tell me what is the non-hypothesis in this situation?
The coin is fair.
Coin is fair.
Yes. How about P? So when we talk about the hypothesis, we always talk about the parameters of interest. So for the non-hypothesis, what is the value for P?
0.5.
P should be
0.5, right? So if this is, oh my.
Assuming the H naught is true, that is P of H. P of T.
I think professor can close his video streaming. Maybe it's better for his internet.